All right. Welcome. Last time we talked about logistic regression.
Thank you.
You're welcome. Oh, thanks, Jeff. Thank you. All right, have fun. See you.
Regular pages. I must have not got stapled.
Oh, okay. Sorry about this. It's not good luck. I'm sorry. Okay, so last time we talked about logistic regression, and that was basically the way we derived this was by saying, well, what naive Bayes, learns P of x given y, and P of y, and you put this together to get P of y given x. And in order to do this tractably, we make the naive Bayes assumption. Well, it turns out in certain cases, this P of y given x, actually, if you do naive Bayes, you actually get a very interesting formulation. You actually get a linear classifier. In particular, in the Gaussian case, which is something you will prove in the homework, this will have a very specific form. It will have the form 1 over 1 plus e to the minus w transpose x times y. And this is called a sigmoid function. And so, well, one thing we thought is, well, if it has that form, anyway, why do we fit this function by actually fitting P of x and y? Why don't we just instead assume this form and then actually optimize the likelihood for P of y given x? This is what we really care about. Ultimately, what we really care about is making the prediction of y given x. And so we looked into this. So is my mic on? I feel like it's not on. Is it on? Thumbs up, thumbs down. No, it's not on. One, two, test better? All right, okay, good. Yeah, please, if the mic is off or if I start speaking German, let me know. So it happens occasionally. So then we said, okay, well, let's do this, right? Let's go over our data set and do maximum likelihood estimation. That's basically sum of all our data and try to maximize P of yi given xi. And so we maximized the following, maximized over w the product over all points, P of yi given xi. We took the log, we did all the stuff, and eventually what we arrived at is a loss function that, well, I know it by heart actually. We sum over 1 to n, you take log of 1 plus e to the minus w transpose xi yi, and that is what we want to minimize. Okay, and so beforehand, whenever we minimize something, we got a nice closed form solution, like when we did map and MLE. This time we did map and MLE, and we arrive at something like this, right? And we don't know how to continue at this point. By the way, please close your laptops. Thank you. Well, not all is lost. So the nice thing about this, that the problem is, we now have this function, we don't really know what to do. But the nice thing is this function is actually very well behaved. Right? And it turns out it's actually continuous and it's differentiable. And actually turns out it's even convex. So what we do is we call this thing here our loss function, our loss of w. And so we can just view this as an abstract problem. We have a function of w and we would try to find its minimum. Okay, this is something you've done ever since high school, I believe, right? It's basically this just, good old analysis. Given a function, where does it have its minimum point? All right, any questions at this point? Some people asked me some interesting questions last time that I just want to relay to everybody. So I make this point that P of y given x is actually, that's what we really want to minimize. And so it's actually, logistic regression seems to be the better thing to do, instead of naive Bayes, right? So then the obvious question is, why did we spend 3 lectures, now you're talking about naive Bayes, if you should just be doing logistic regression, right? And actually, it's not so clear cut, right? It's not that logistic regression is always better than naive Bayes. And the reason is quite simple. When you don't have all that much data, let's say you're in a regime, like for example, you do spam filtering, right? Well, there's actually 2 reasons. There's 2 reasons why you want to prefer a naive Bayes for spam filters, for example. The first one is that naive Bayes is really, really fast, so you don't have to train anything. Here, we still have to figure out how to find the minimum. The second thing is, imagine you've only seen a couple of emails, right? The problem with logistic regression is you have a very, very high dimensional space, and you're trying to predict y given x. And there's infinitely many hyperplanes. And so essentially what it will do, it will be extremely biased towards these few emails that you've seen, right? So if you just have very few data points, it will actually not give a very good classifier because it will essentially overfit, and we will talk about overfitting very soon, right? Naive Bayes is not so prone to that, and the reason is because here you make a Gaussian assumption. You add additional knowledge, right, that you put in. You're saying this distribution has to be Gaussian. And by doing this, you're reducing the number of hyperplanes that you could possibly learn drastically, right? That's a bad thing if you have a lot of data. If you have a lot of data, then why would you reduce the number of hyperplanes that you can learn, right? Just learn the best one that separates your data. But if you have very, very little data, if you only have a couple of data points, right, then there's just too much degree of freedom. And you're going to learn something that is, it overfits too much to these few data points. Then actually, naive Bayes is actually much better. Now, it turns out for spam filters, most people are pretty lazy, and they very rarely click on spam versus not spam. And one thing you want to do is you want to give them a good spam filter right at the beginning when they try out your product for the first time, right? So actually, naive Bayes is actually typically what people use in this case. So it's still, it's still used very heavily. It's just when you have a lot of data, then actually typically logistic regression is the way to go. Any questions about this? No? All right. So here today I will I will look into this abstract problem of saying I have a function L of W, and I want to minimize it. And this is a very general thing. And it turns out that many machine learning algorithms, not just logistic regression, many machine learning algorithms can be written as in exactly this form, right? And we call this our loss function. So what this basically does, it measures how many points do you get wrong, right? That's essentially what this function does. So, all right, so what does this function look like? I told you it's continuous, differentiable, and convex. So it kind of looks like this. Something like this, right? So it's kind of like a bowl. That means it's convex. It doesn't have any jumps in it. That means it's continuous. And we can compute the derivative, so it's differentiable. And we would like to find this point here, right? That's our target, okay? So the way this works is there's many, many, many different ways of doing this. And optimization theory is its whole own field of mathematics. But I will show you today the basic principle, and essentially most algorithms don't deviate too much from that. So here's the idea, right? What we do is we say, well, initially we really don't know where this minimum is. We have no idea which parameter setting is the minimum, right? If we knew it, if we had a closed form solution, we'd be done. We don't know. So what do? We just assign W to anything we want. It doesn't matter, right? Whatever. Just make it all zeros, so all random values, right? Put in your birth date, encode it in the weights of W. So you have now some point here, which is my initial W0. Okay, so basically, this here is my axis. This here is W, and this here is the loss of W. Okay? So initially I just set, my loss to anything I want. It doesn't matter. And so now the important thing is, I would like to know which direction does the minimum lie, right? And so basically what I need to find is like some direction that I want to walk into. Let's call this S, right? And I basically want to, identify which direction do I have to go, and then I take a small step in this direction, and then I get a new point, and then I look again. right? That's the basic idea behind hill climbing. In this case, we're not climbing, we actually try to find the minimum, so function minimization. Okay, any questions at this point? All right, yeah, question. Is there more handouts? There should be more handouts. I printed enough, and there's a lot of empty seats. Who has 2 handouts? Who has more than 2? Sorry? Oh, this whole thing hasn't got any? Oh, I'm sorry. Wait, but I'm confused. Are they somewhere? If you know someone who has the handouts, please point in that direction. people are blaming people. Is that true? Oh, I'm sorry. How is that? Wait, that's really bizarre. I had 300 copies. There's not 300 people in this room. No, someone leave with a big sack full of notes. I'm sorry, I don't know how to resolve this. Yeah, there's nothing I can do. I'm sorry. All right, I will guard them more carefully next time. They will be online. So, yeah. Oh, but then I have a mad rush at the beginning. Okay, well I could put them in the entrance. All right, find some algorithm. Okay, okay, good. No, let's do something. If anyone has suggestions, please post them on Piazza. If you have some convergence rates, actually, I appreciate it. Okay, good. All right, so we have this function we want to minimize. The problem is we don't know what this function looks like, right? So we know it kind of looks like this, but it could be nasty, right? And we also don't know how much of a step we should take, right? If we take too much of a step, then we may overcome it. Right now it looks like this, but the function could also look like this, right? So then if we are here, we take a step that's too large, we actually end up over here, right? Which is not what we want. Or if we take a step a little bit too large, we are over here, which is really, really high, right? So how do we find this minimum? And the assumption is, what we do is a very, very simple trick. It's basically we say, well, this function is really, really complicated, and we don't know how to minimize it. But let's just assume the function was easier, right? It was really simple. And for example, linear or quadratic. And if the function was linear or quadratic, we could actually find the minimum very easily, right? And so basically what we're doing is we say, well, here, let's just fit a line and say, assume this here was a line, right? Well, if this function was just a line, then it's easy to figure out in which direction you should go, right? Just go in the direction where it goes downhill, okay? And so you just take a step in that direction, and then you fit a line, and you basically look at this again, right? So that's the idea. More formally, what we're going to do is we're going to use Taylor's expansions. And who's heard of Taylor's expansion? Raise your hand. Oh, perfect, beautiful. All right, so Taylor's expansion is quite simple. It says you can approximate this function L by saying L plus S is roughly the function at W plus the gradient at W times S. Right? So, sorry, this is just times S. Sorry, what's going on? Okay, good, thank you. Right, so basically what we're doing is we say at this point, like what Taylor expansion basically says is this function is continuous and it's differentiable. What does that mean? That once again, if you're a teeny little ant and you're sitting right here, right, what you would think is that the function is actually a straight line, right? If you're just small enough, right? Because the function is smooth, right? If you just zoom in enough, right, at some point you will actually not feel the curvature anymore, right? And this is exactly the effect of the planet Earth, right? So it's globally has a huge curvature, but actually if you just look here, it actually looks damn straight, right? So that's basically what we're doing here, right? We say locally, actually this function, the approximation that the function is linear is not a bad approximation. right? And in fact, this is not just the only thing you can do. You can actually say, well, we can approximate even better if we add a second derivative. And then we basically just say, well, this is plus 1/2 S transpose H of W S. Right? So you basically say, what's the function value at W? And then I go a little bit in the direction of S. If S is just small enough, then it's linear. Right? And if S is a little larger, then I guess a better approximation actually is if I take the second term into account as well. Then what I'm doing essentially, I'm saying the function is not just a line, it's actually a parabola locally. Right? So it looks like a parabola. Okay? Any questions? Do people know what the H of W is? It's the Hessian. Who's heard of Hessians? Outside of history. Okay. So the Hessian basically is a matrix that basically just says the ijth entry is the derivative with respect to, well, let me write it down. So Hij is the derivative, of L with respect to Wi and Wj. Right? That's actually the second derivative generalized to functions with multiple inputs. Okay, and so actually Taylor approximation says if we just we take the first derivative, the second derivative, and the third derivative, and so on, we could eventually make it arbitrarily close if the function is differentiable enough. We will stop after first and second derivative, right? Because the reason is the first and the second derivative, these are actually, if we just look at the first derivative, it's a line, and we know how to minimize lines. And if we look at the second derivative, it's a parabola. And parabolas are also very, very easy to minimize. In fact, we can do it in closed form. Right? So those are this approximation basically is simple enough that we would know how to minimize that function. Now, the trick, however, is this approximation only holds when S is really, really small. Right? So we can't just say, oh, the function is roughly this, let's minimize this thing on the right, right, and then we're done. That's not going to work. Right? So for example, if you have this parabola assumption, what you would do is you would jump here, and then you would actually find the minimum here. Well, that's obviously wrong, right? So the assumption only holds for small steps, right? So basically, the way it works is we approximate the function as the Taylor expansion. We take a step towards the minimization of the Taylor expansion, and then we approximate it again, and we just repeat that process. And that's basically how these function minimization processes work. Okay, any question? Yeah? Why don't you make S really, really small and?
Just use the linear version. Why do we have to take the parabola version?
Why don't we just use the linear approximation? Okay, good question. So he says, this Hessian, I don't like the Hessian, right? What have they done? Why don't we just use the linear approximation? If S is small enough, that's a sufficiently good approximation. And that's actually what most people do. All right, there is a reason why you may occasionally want to use the Hessian. The reason actually is that you have to take many steps. And so sometimes it's the case that you would have to take 10,000 mini steps, or you take 2 steps with the Hessian. So it can be a lot faster, right? But it's not always the case. And we will get to this in a minute. Okay, so the first gradient descent, the first step is gradient descent. A lot of you, I'm sure, have heard of it. Is the most general framework of minimizing a function. That's essentially exactly what you just proposed. Gradient descent, basically what we're saying is this vector S that we want to add to our function to go downhill is just the negative gradient. Right? It's just the gradient at W times a small step size times negative. Sorry. So we had, where is it? Sorry, one sec. So here we had this little picture that we basically have our W0, and then we take a step S. And here I'm telling you in gradient descent, we just say S is the gradient at W times some small learning rate, and then we negate the whole thing. And so why is that the right thing to do? Right? Well, if you just look at this approximation, then it's very, very easy to show that actually, if we take this step, we will always take a step down. We will always reduce the function value. Let's just test this for a second. So our loss function L of W plus S, which is now this term here. So plus minus alpha G of W. Okay, so now we have our original W. I'm telling you, this here is the step. This is basically this step in which we want to take from our original W. And I'm claiming this here should be less than just L of W. So it should be less than the value that we started from, right? If that's true, then I showed you that by taking the step, we went downhill. So we know that this is roughly, if alpha is small, we can make this as small as we want, then this here S is small. So we can make alpha small enough that the Taylor approximation holds. Then that is L of W plus this here, so I guess minus in this case, minus alpha times G of W, this is S, times G of W. Okay, so all I did here is I plugged in minus alpha times G of W into the S up here, right? And then we get this term here. Raise your hand if you're still with me. Awesome. And, well, what is that? Let's just look at the sign of this thing. This here is the square of a vector. So that's greater than 0, right? Alpha, we just choose alpha to be small but positive. So let's do this. Alpha is greater than 0, right? That's a scaling parameter. So that whole thing is still positive. And then we have a negative here. So this thing here is negative, right? Less than 0. So we take the our vector L of W, our loss L of W, and we subtract something from it. So that's clearly less than L of W. Okay? So what I just showed you is that no matter where you start, right? No matter what your starting point W is, you just compute the gradient, multiply by the small numbers, and if you subtract that from your W, you're taking a step downhill. And so if you do this often enough, you will eventually come to the minimum. Right? So that's basically the idea. Right? Why will you eventually come to the minimum? Wait a second. Why is that guaranteed? Can anyone tell me? Yeah?
Because the function is convex.
Because the function is convex, right? So that's right. So if the function was not convex, it could look like this, right? Then if you start here, you go downhill, go downhill, go downhill. Here at this point, what happens here? Here there's a stationary, here the gradient is 0, right? So you stop. Right? So you think you're done, but actually, you know, this can be arbitrarily deep here, right? You can actually be pretty bad. But because the function is convex, and I think this was actually on the placement exam to show this, you don't have to worry about this, right? So you keep going down, keep going down, keep going down, and eventually you will stop. Why are you going to stop? Because at the minimum, the gradient is 0, right? So at that point, you basically know that you found it, right? You're not moving anymore. Okay, any questions about this process? No? Yeah?
How do you pick alpha?
How? Sorry?
How do you pick alpha?
How do you pick alpha? Good. I was waiting for that question. That's exactly right? How do you find alpha? We said alpha has to be so small that Taylor approximation holds. Well, how are you going to do that? Right? And, well, one thing is you can just err on the side where alpha is too small. Right? If alpha is really, really small, then Taylor approximation will certainly hold. The problem is then you're taking tiny, 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 tiny steps, and it will take forever, right? And it may take your whole lifetime to minimize the function, right? So then actually it's probably much better just to wait a little bit and buy faster computers in 10 years, and then just start then. So the question is, how do you find this alpha? And this is actually something that the community has thought about for a long time. And I think when I started my PhD, it was still considered a dark art. And people thought, well, you just use voodoo, right? So everyone had their own kind of mechanism. Right? Well, you know, eventually, I start out with 0.1, and then eventually I decrease it, right? And you had your secret sauce. Now, fast forward a little bit, it's actually very well understood. So for once, a really safe way of doing it is basically just saying alpha is some constant divided by t. But t is the number of updates you've already taken. If you do this, then it will provably converge. And the reason is, no matter what your constant is at the beginning, but eventually this will become so small that Taylor series holds, and so you don't have to worry about it. And you can make your constant large enough that it will converge eventually. That's not very good, because it's still very, very slow. In the last 2-3 years, people have actually made some sufficient progress here. And damn it, this is horrible. Okay. And nowadays what people do is actually much more sophisticated. And I want to quickly go into this. It's called Gras. Gras was only invented a couple years ago, but it's basically really taken the community by storm. And the idea is very, very simple. The idea is, well, here's how it works, right? If you have it depends really on what your function looks like, right? If your function looks like this, and you're here, right? You want alpha to be very, very small. Because alpha is too large, you're going to jump over this thing here, right? If your function, on the other hand, looks like this, right? Then you want to have alpha pretty big, right? Because your gradient point in this direction, you want to take huge steps, right? It's not so steep. And so, essentially, the mechanism, I'm just going to explain to you as a heuristic. I'm not going to, but it turns out actually you can derive this very, very nicely, and it's very principled. The idea is very simple. What you do is, as you do your optimization, you keep track of the gradients that you've had in the past. And basically what you're doing is you say the following. Well, imagine you have different features, right? So you have some features that are basically tracked in, you have medical records. Some are tracked in millimeters. So you hide in millimeters. That's a very large number. So I don't know why you want to do this. But, let me give a better example. Let's say I have spam filter. And I have word counts, right? Some words will be very, very common, right? Like the and a and so on, right? These are stop words. But even, banana is going to be much, much more common than maybe hippopotamus or something, right? So words have different word frequencies. So what happens is that basically the gradient will vary a lot across the different features, right? And so really there isn't really one good learning rate for every single feature. So ideally, for each feature you'd have a different learning rate, right? But now we made the problem even worse, right? Before we just had one learning rate. How do we fix this one? This was a dark art. Now we have to fix 1,000 or maybe 1,000,000 learning rates, right? Every single dimension should have its own learning rate. And so here's what Gras does. It basically says, as we keep optimizing, I put it in my notes. That's right. As we keep optimizing, what we do is we have this algorithm that we say, we repeat, we evaluate, L of W, the gradient of W, G equals DL dW, that's a vector, right? And then what we had before is we said, okay, W becomes W minus alpha times G. Right? So that's the gradient descent algorithm. And we don't know how to tune this alpha, so here's what we do. We do the following. We start with some vector S, which initially is 0. And here we put our for loop. And then every time we compute a gradient, we say S becomes S plus G squared. And can anyone explain what I mean by this? Where are the Julia people? I take every single entry and square them. Okay, so you can either write this as this, or or you can write it as this. G. Right? So basically, you just take every single entry and square them, but you keep it a vector. You don't sum over them. Okay, so it's not G transpose G. is G dot star G. So what you're doing is you basically keep track of, on average, like how large the gradient was in past steps. And then what you're doing is you take the gradient that you have, and element-wise, you divide it by the square root of the sum plus some epsilon. So essentially what this means is, when in the past I had a feature where the gradient was very, very large, right? Then this is very, very large, right? Because I square it and I sum over all the different changes. So that means if I divide the gradient by it, the step size is going to be really small, right? So if I have very steep, in some dimensions, I will have very steep surfaces. For those, I take small steps. In other dimensions, I have very shallow surfaces. I take large steps. Okay? And that has really become kind of, the beauty of it is you still have some constant here that you can set, but it doesn't really matter. You can just set it to 1, and then you just get rid of it, right? Ultimately, it sets itself, right? So basically, it takes past gradients, and it learns how to set the learning rate. Any question? Yeah?
I think you switched G and S between the board.
Oh, I'm sorry. Is that true? Oh, I see. Oh, see, my notes are wrong, actually, right? Oh, see, in the notes, it should be SS instead of GS. And in the notes, I call this S and this SS, which I blame on momentarily insanity. Okay, any more questions? Yeah?
How do you choose epsilon then? I mean, what?
Oh, why is epsilon? Oh, it's just because in case something is 0. Imagine you have some feature where you just have no gradient, ever, right? That also means that feature doesn't matter, right? But that means S squared would be 0, and you would be divided by 0, and everything would blow up. So you just add some constant to it, and then you get a very large learning rate. It probably doesn't matter because the gradient is 0, right? Yeah, good. I mean, in some sense, because you just added this, right? The gradient must be 0 here, so it doesn't actually matter what you do in that case, right? Good question. Yes? Any more question? So epsilon is just 10 to the minus 5 or something. Oh yeah, at the very back. Yeah.
We talked about, you said that we will find the minimum, but this really converges to the minimum, and so we need to and so it's only asymptotically convergent on a Dex number line, right? So we have to talk about then based on how our data looks, what our convergence criteria are going to be also. Right?
Oh, good. Right. So the question was, well, actually, we're just getting closer and closer and closer. And as we get really, really close to the minimum, what's going to happen? The gradient's going to come, become 0. Right? Here it is 0. So here it's going to become really, really, really small. Right? So what will happen? We actually take really, really small steps. So will we actually ever really get there? Right? So when should we stop this whole algorithm? And so you do exactly this. You basically keep track. You say, this here's my t plus 1, this here's my t. And you say you stop if the norm between t plus 1 minus wt is less than some small delta, then you break, then you stop. Right? So you usually always have some cutoff, but you say, if my weights have not changed in the last round, then I'm stopping. Right? The important thing is, and this is really something that people didn't realize for a long time, is people use these concepts on optimization theory and mathematics. In optimization theory, they're really concerned of getting exactly to the minimum by accuracy up to 10 to the minus 10 or something. In machine learning, we don't care about this, right? Because ultimately, what we want to minimize essentially is just the 0-1 loss, right? At the end, we just want to have good predictions. And if you get a little bit closer, it probably doesn't make any difference, right? So, this delta can be sufficiently large, actually. Right? Okay, any more questions? Okay, good. So that was gradient descent. Now come in the Hessians. So gradient descent is really nice. The only thing is, and this is actually the step that you said, it's really nice getting close to the minimum, but once you're in the vicinity, it slows down. So most of its time, almost all its time, it will spend, close to the minimum. Okay, because that's when the gradient is small. Right? So the question is, can we somehow speed this up? So like once we are close to the minimum, can we get right to the minimum? Up to some delta that we can stop. And this is exactly where the second order approximation comes in. All right, whatever. So far what we said is, we just approximate this a line and basically just said we take a step in the direction of this line, the slope. Now we're basically going to take a parabola. And so, wait a second. So the idea is quite simple. We can just take exactly this function here and just minimize it with respect to s. Right? We say, wait, Taylor's approximation tells us our function is approximately this. Where now don't cross this out anymore. Can I just minimize this? This is a quadratic function. And what's exactly the step size that I would have to take to minimize this function? So what I'm saying is, I have some w here, I find this parabola. Now I pretend my function really is the parabola. And parabolas you can minimize in closed form, so I can just find the minimum of the parabola. Right, that's what I'm going to solve for. And this here is my s. For the difference from w that I have to add to get right to the minimum of the parabola. And once I'm here, then I again fit a parabola. I find a minimum. Again, I fit a parabola, and then I'm done. Right? Newton's method converges super fast, blazingly fast. Right? You just need a couple of steps. Like if you take 10 Newton steps, you're going to be there up to a numerical accuracy usually when you have low accuracy numbers. Like in machine learning, a few Newton steps typically get you there very, very quickly. So let's just quickly do this. So you want to minimize this with respect to s. So minimize this function with respect to s. And what do we do? What do I do when I minimize a quadratic function? It starts with gray and ends with the end. I think someone said a gradient. So I compute the gradient with respect to s. This here is 0. This here is g of w. This here is, now I have to take matrix gradients. If you're not familiar with matrix gradient, look at the matrix cookbook. I think I linked to it from the homepage. So that's h of w times s. And we want to set this to 0. So this here is the gradient of this function with respect to s. That's 0. What do we do? Well, it's quite simple, right? So we just put this on the other side. So s equals g of w minus g of w. And to get this function, this matrix over there, we just take the inverse, right? H of w inverse. Right? So we divide by this. That's what we have to do. So Newton's method, what you do is you just take your random vector w, you compute the gradient, and you compute the Hessian. And you multiply the gradient with the inverse Hessian. And that's what you add to your function value. And that basically gets you down really, 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 really quickly. Right? So Newton's method is awesome. There's however one downside. And this downside is most of the time, it doesn't work at all. So most of the time what happens is that when you have a function that's really, really flat, right? What you're now doing is you're approximating that with a parabola. And that parabola could look like this, or something like this. And now you're taking a really large step. Let's say my function looks like this or something. Now you're taking a really large step, right? This here is my s. And if you take really large steps, Taylor approximation doesn't hold anymore, right? And so what you're doing is you're shooting off into no man's land, right? Or let me give you an even better example. Let's say I have a really skinny function like this, right? I have a function like this. This is my convex function, right? So it could very well be that my parabola that I'm using here looks like this, right? Approximating this way. So I start here, I jump all the way here to that minimum. Right, now I end up here, right? Now I approximate it again with a parabola, and I end up here, right? And I'm spiraling out of control in no time. So Newton's method really only works if you're very, very close to the minimum already, right? And your function is not. Well, I can show you some examples. Why don't I show you some examples? So the best, typically what I recommend people to do is do gradient descent for a while, and then just before you end, take 2 or 3 Newton steps, right? And then you're basically, then you're sorted, right? Because then you're basically at the minimum. Any questions? What people, by the way, also do is they sometimes just take the diagonal of the Hessian. That also works reasonably well. Those are called second-order methods. Or there's conjugate gradient that approximates it. Yeah?
Why don't we take a small step size alpha for the radius?
Well, in some sense, you're solving for the whole thing, right? So it's no longer, if you downscale it, I think you still wouldn't get any convergence guarantees, actually. In some sense, the benefit would be gone. What is this? This is not me. Oh yeah, okay, good. All right, so here's a, how much time do I have? Okay, so first I just want to show you a little. So first a little example of just good old gradient descent. So here's my function. And the red point is where I initialized it. And this is actually a quadratic function. So the minimum is actually here at 0, right? And so now I can basically put in the different step sizes and see how long it takes me to converge, right? And so the first thing I can do is I can just set the step size to 0.1, right? And now you can see the different steps. I don't know if you can see these. Can you see them? It basically takes all these red lines here, from here to here, basically is a step, right? So all these different things. So it took all the way 83 steps, right? So it took 83 steps to go from here to here. And then it basically converged up to some delta. I could do the whole thing again with a smaller step size. Then actually it never converges. At some point I just said maximum number of iterations has reached. So I never get there, right? If I make my step size larger, so let's say I just do 5, right? Why not? Then what happens? This happens, right? So here's my function, right? And this here, I basically, you have to see, this here's my function down here, and this is kind of Jupiter, and this is, like Neptune or something. Be way out there in outer space, right? Oh my gosh. Come on, where is it? I see something, I'm hopeful. Right, so I'm really, really out there. All right, so you get the point, right?
Hey, isn't your thing a Google all?
Sorry?
The scale at the top, it's 10 to the 100.
Oh yeah, 10 to the 175. Great, yeah, that's more than electrons in the universe, right? So we are really, really out there, right? So I didn't even take my step size that large, right? I was just a little bit lighter, right? And bam, right? Did I shoot past the minimum, right? So setting the step size is important. I can also show you some Newton steps. So here, GRD demo 1 Newton. So here's another example. This is a beautiful function. And now Newton, the beautiful thing about Newton's method, I don't have any step sizes to choose from, right? So I can just, I run it and I converge. So we can first say, okay, well, let me just start at 0.3, right? And at 0.3, I converge with 9 steps. right? Well, I'm pretty accurate here, very, very accurate. If I, say, let's say oh, this is 0.3, I start up here. Okay, this is pretty steep. So if I start at, whatever, at 2, right, then I would only take 8 steps, and I'm actually here, right? And the nice thing is that every single step, you actually usually get 1 digit of significance, of accuracy. What if I start at 9, right? So that means I'm starting over here, and I do my Newton search, right? Then, bam, right? What happened? Well, I'm actually, oh, I'm still fine. Wait, I'm still fine. This is amazing. Okay, let's do 7. Let's do 10. Ah, okay, now I diverged. Right, so now actually if you zoom out, if I try to zoom out, which I can't. So one thing you can see, the red line actually, okay, I can't zoom out, I'm sorry, I don't know what happened. Basically I'm again in outer space, right? So the difference is with Newton step, the equivalence in some sense, like with gradient descent you have to set the step size right. Newton step only works at certain starting points, right? The good news is you can check very easily if you made a mistake, right? If your loss is suddenly a lot larger, then you know, oops, right? Newton step doesn't work here yet. Just keep doing a few more gradient steps. All right. I can show you the same thing one more time in 2D. No. Sorry, once, oh. Ah, shoot. All right, here we go. Here we go. So what you can see here is actually a function that I'm trying to minimize. All right. So what you can see here is basically the black line is basically gradient descent. This is my function. This is basically my function value. This is the number of steps I'm taking. And what you see is the gradient descent very quickly gets close to the minimum, right? But then takes forever to do this last little bit, right? To get from here to here, right? Takes 100 steps, right? So that's exactly the problem with gradient descent, right? So you get close to the minimum relatively quickly, but then it just takes forever to finally get there, right? So Newton steps actually is very, very good, right? In just a couple steps, actually, it's really at the minimum. If you look at the plot here on the right, you actually can see this is the function. Here's where I started. So gradient descent takes these, gradient descent is green one, so it actually takes 1 step here, and then over and over and over, and then very quickly it's actually close, but then here it actually takes forever, right? Whereas Newton steps actually very consistently gets towards the minimum. And I don't know if you can zoom in any further. Yeah, so Newton step basically just takes from here 1 more step, whereas the gradient descent here probably takes 90 more steps, right? So if you're close to the minimum, you want to take Newton's method. Let me do one last one before you guys leave. This is the, here's basically if I started at a bad point. So here's the same function. And again, you see here, I'm actually, the red line is Newton steps. So my function is down here. And very quickly, I'm out of space, right? I basically completely blew it. And what happened is I just started as, so here's what Newton step does, right? So gradient descent very nicely goes to the minimum, and Newton step is like, oh my gosh, right? Like it's like, So what do you do in such cases? And the answer is you just take a few steps with gradient descent. And then you do Newton steps, right? So here's what I did. I took a couple of steps with gradient descent, and then I switched over to Newton. And then I'm OK again. All right? So please remember this. The main take-home point, when you do gradient descent, do adaptive gradient to the other grad. And when you get close to the minimum, so maybe after a couple 100 steps, or 10 to 100 steps, switch over to Newton's method, and then you converge in no time.